All right, in this next video, we're going to take a look at dynamic memory allocation using new and delete. You can allocate and deallocate individual objects with new and delete. You can also allocate and deallocate arrays of objects using new with square brackets and delete with square brackets. So any kind of container, such as a list, a stack, a tree, a hash table, what have you, is a complex structure that grows and shrinks while the program is running. Okay, it's not of fixed size, such as an int or an array of 5 double or something like that. We have to be able to dynamically allocate memory on the fly and then deallocate that memory later when we're finished using it. The region of memory that's available for dynamic allocation is called the heap, or alternatively the free store or the dynamic data area. These are all just equivalent terms for the same area of memory. So to allocate one object's worth of memory from the heap, we use the new operator. Now, new is a word, but it is syntactically treated as an operator symbol. After we've allocated the object and we no longer need it, we can give the object back to the system, give the storage back to the system by using delete. All right, so if I want to allocate some object of some data type, like an int or a double or a fish or a manager or whatever it might be, I say, give me a new, and then the data type name. And what the new operator does is to return a pointer to that allocated storage. I need to save that pointer that new returns into a pointer variable that's been declared to point to the data type that I'm attempting to allocate. After I use that object in whatever way I wish to use it, and I don't need that memory any longer, I need to say delete P to deallocate the storage for that object so that I can reuse that storage for some future object. So that's kind of the general syntax. And by the way, if you don't, if you fail to delete, this gives you what's called a memory leak bug. And these memory leaks are often very difficult to detect because what will happen is that your system will kind of gradually and initially perhaps imperceptibly slow down and eventually kind of grind to a halt. So we can allocate a fundamental data type, such as a char, short, int, long, float, double, extended, long double, either without initialization, in which case you have an undefined value in that storage. Or you can, if you wish, specify an initial value using parentheses or curly braces like we've done in the past for local automatic variables. So here is some kind of trivial and very unrealistic code illustrating this idea. I've declared 3 pointer to int variables here. P1 is a pointer to int, P2 is a pointer to int, P3 is a pointer to int. And when this code runs, I'm going to allocate a new uninitialized int on the heap. I get back the address of that uninitialized integer's worth, int's worth of storage, and P1 is set to, or is initialized to, point to that int's worth of space. Later on, if I display what is contained within that space, what's at that space that P1 is pointing to, I'm going to get whatever garbage is sitting at that location. When I allocate a new int, I get 2 bytes, on our systems that would be 4 bytes, 32 bits worth of memory allocated. And that memory is going to contain some pattern of 32 bits, but there's no way of knowing in advance what that pattern might be. So when I display that pattern of 32 bits as an int value, I'm just going to get some garbage or uninitialized or random number. I can use either the original C++ style with parentheses or the more recent C++ style with curly braces to specify a specific initial value that I want for that newly allocated chunk of memory. So when I display star of P2, when I display star of P2, that will, when I display, I know I can highlight this. When I display star, all right. When I display star of P2, that will display the integer value 3, and star of P3 will display the integer value 7. Now, at this point, I'm finished using my 3 ints worth of memory on the stack, and so I am using delete to give back that memory. Sorry, I said the stack. I'm finished using that memory that's been allocated on the heap or on the free store, and I'm using delete to give that memory back. Now, in practice, since this is just the main function, when you return from main, any storage that was allocated on the heap for your program is going to automatically be deallocated anyway by the underlying operating system. So you could argue that these deletes here are sort of redundant because they just automatically happen when my program is finished. But I want to emphasize that you need to take responsibility in more complex programs that anytime you allocate something with new, sooner or later you had better deallocate that thing with delete. This is particularly true of things like lists or trees that grow and shrink and change shape for extended periods of time while your program is running. All right, so as we showed, you can use either the parentheses or curly braces to provide specific initial values. You can also use these empty to get default values instead. And it turns out that for all of the fundamental data types, the default value is a 0, converted to the appropriate data type. So if you're allocating a new char, the value 0 will be treated as a null character. If you're allocating a new int, then that will just be the integer 0. And if you're allocating a new double, that will be a floating point, 0.0. Here we're showing this default initialization style for a couple of int objects. All right, so P1 is a pointer to an int, pointing to a newly allocated int with a default value, which is 0. Likewise, P2 is pointing to a new int initialized with a default value. Again, that's 0. Now, if I write this declaration, so I say int I and then open and close parentheses. Is that attempting to create a variable called I initialized to a default value of 0? Well, unfortunately not. It turns out that this is a special case that predates C++. Here, the parentheses are interpreted to be function call declaration. And so what this last line of code in here is actually saying is that I is a function that takes no arguments and that returns an int. If I wanted to have a variable called I of type int initialized to 0, I would have to actually put a 0 between the parentheses here. Okay. Now, it is also possible to allocate and deallocate arrays of objects using the square bracketed forms of new and delete. And here's just syntactical illustrations of that. If I wanted an entire array of n objects of some type, I say new and then the data type name, and then in square brackets I give the number of items that I want. And that has to be an int. You can't have, a floating point array, and it should also be a positive number. You might be able to get away with 0 if you want a pointer to nothing. Honestly, I'm not sure about that. It would not be very useful except for some kind of trickery anyway. Now, the thing is, if you do use the square bracket form of new to allocate an array of things, you need to also use the square bracket form of delete to deallocate that entire array. And this will have the effect, assuming that you're allocating objects of some class data type, this will have the effect of properly deallocating all of the memory associated with all of the objects in this array of objects. Frankly, people don't often use dynamic allocation of arrays because nowadays in the standard library we have the vector data type, which gives you a safer and cleaner syntax for dealing with arbitrarily sized arrays. Now, if the new operator is unable to allocate storage, by default, it will throw what's called a bad alloc exception. And that will cause your program to die. When we are on a modern system, such as Linux or Mac, which is a version of Unix, this more or less doesn't happen. In plain ordinary Windows, which does not have such good memory management, you can actually run out of storage, and the program will die because of a bad alloc. There's a special pointer constant called null pointer. You can use 0 as an alternative for null pointer. That can be used to initialize a pointer to something where you haven't decided, where you haven't actually done a new operation yet in order to allocate space. Okay. Now, about delete. The heap is the area of memory that new obtains memory from and that delete returns memory to. And this is a very intricate, I highlighted the wrong thing. This is a very intricate data structure. And as usually is the case in C++, wherever there is a choice required between efficiency versus safety, C++ always chooses efficiency. This means that C++ will not double check that things that you're trying to deallocate point to things that have been previously allocated. If you don't properly connect up each new and delete and each new square bracket with each delete square bracket, you can easily create a corruption in your memory, which very likely is going to cause your program to crash. Okay, so in other words, if you allocate memory with new, you must deallocate that memory exactly one time with delete. If you forget to do that and your program continues running, you've created what's called a memory leak situation. And if your program produces compounded memory leaks, at some point you'll start noticing that your program is slowing down. You may even start noticing that your entire system is slowing down. And at a certain point, your program and or your entire system may crash. Okay? Deleting anything more than one time will corrupt the heap and very likely cause your program to crash either immediately or later. And if you try to delete any pointer that you did not get back from new, that will also corrupt the heap and at some point cause your program to crash. Now, it turns out that if you do a delete on null pointer, or if you do a delete on the value 0, that's okay, and nothing actually happens. Okay, so dynamic memory allocation is very powerful in that it allows you to ask for arbitrary amounts of memory at runtime, in case you don't know the shape of your data in advance, prior to your program running. On the other hand, because there's basically no safety net, memory allocation with new and delete is also kind of dangerous and should be done extremely carefully. Okay, let me finally show you a little example program to illustrate kinds of bad things that can occur. This is called the new prog.cpp file. And actually, I did not upload this to Canvas, but you can just go ahead and create it for yourself if you like. Okay, so in here, we're saying include AutoStream using namespace standard, int main, open curly brace, etc. And here I have declared the variable pi as an uninitialized pointer to int. All right, so this pi variable here, this pi object, just contains some garbage value at this point. And what I'm attempting to do in this cout statement is to follow that random address, that garbage address, to some integers worth of memory and display what's at that location. Now, because pi is just some random, uninitialized, unknown value, attempting to follow that pointer may accidentally work, or may actually attempt to access memory that's outside of the boundary of your program's memory, and in that case, your program is going to crash. So let's just see what happens on my machine here. I'm going to say g++, new prog.cpp, call the output program new prog, and here it is, new prog. Okay, so, whoops. So apparently, that did attempt to access memory that is outside of the region of memory controlled by my program. And when you see this error message on a Unix or Linux system, segmentation fault, that almost always means that you have attempted to use a either an uninitialized pointer or an incorrect pointer that's trying to get outside of your program's memory. All right, so segmentation fault means that you've got some kind of pointer bug. All right, let's modify the program. This time, I'm going to allocate a new int for pi to point to. All right, so I'm allocating a new int. That means that the pi pointer variable will be initialized here to point to this newly allocated int. However, that newly allocated int itself, as I said, it's 32 bits, it's 4 bytes, and it's just some random pattern of bits. So we don't really know what we're going to get as the value of that int when we access that int using our indirection or concatenat operator. So let's give this a try. Whoop. I'm using, by the way, an ancient editor called VI because I'm fast with it and it doesn't have a lot of menus and buttons and all that kind of stuff. All right, so I'll compile it again. New prog. And it runs. Okay, and I get 1244. Who in the world knows where that came from, all right? But that's what I happen to get. So let's revise the program yet again. And this time I'm going to specify a specific initial value, 9876. So now when I run my code, I will have an initialized int, and I should be told that that is 9876. And it is. Okay. Whoop. And so now the problem that I have, which it wasn't immediately clear from anything we saw on the screen, that there is a problem. But you'll notice that I forgot to say delete of pi. And so if my main program did not simply end and exit at that point, that memory leak could become a real problem for me as time goes on. And if I continue allocating more values and continue forgetting to delete those values, eventually my program, or for that matter my entire system, may die. So I am going to now say delete pi to properly clean up after that allocation. So I'm allocating with new, I'm deallocating with delete, and that eliminates the memory leak problem for certain. Okay. All right, well, let's carry that one step too far. Let's suppose I mistakenly say that I want to delete pi 2 times. This first one will work, but the second one will fail because this address that pi contains no longer points to dynamically allocated memory. That dynamically allocated memory was already given back. So let's see what happens if I make the mistake of deleting twice. Abort. Okay, so my program crashed. I did not get a segmentation fault error. Instead, I got an aborted error. Because although this time the program was attempting to access memory that was within bounds of what the program was using, that portion of the heap was no longer available for this program to use. And so I crashed for that reason. All right, so when you use new, you must always use delete exactly once. Normally, you would use new in one function, such as a creation function, and you would use delete later in some kind of destruction or close kind of function. This situation here where I'm using new and delete in the same function is really just kind of artificial. I don't need to go through this rigmarole here. Since I'm doing everything in main, I can just say int I is 9876 display I, and then when I return from the function, I will automatically be deallocated from the stack anyway. So I was really just illustrating the syntax and the concept there of the dynamic allocation. There's no necessity in a single function to do what I was demonstrating. Okay, so local variable. If you're just working within a single function, a local automatic variable works fine. Okay, well, that gets us to the conclusion of that material.